Let us continue. A dot plot and a histogram. So we're using two visualizations, a dot plot and a histogram of the mean weights for .500 simulated random samples are shown below. So 500 random samples. Well, as you can see, when it comes to dot plots, you see frequencies on top of each numbers, which shows the grams. So this is the dot plot representing our data. And finally, we are using a histogram to represent the same behavior for the data. Both of them are representing the exact same set of data. Take a look at the graph. It's approximately normal. The same for your histogram. It is approximately normal. So, very well. If we want to use our normal formulas, we're allowed to do that. So question says, well, in the dot plot of the distribution of sample means, what does a dot represent? So we have our dot plots here. This is our dot plot. As you can see, we have dots here. Each dot represents a sample mean. Remember that we took random samples from population and we calculated the mean. So each dot represents the sample mean. Well, let's answer more questions. Question 12 says, imagine we want to estimate the mean weight of individual acorns collected by the students. How could we use the distribution of sample means to make this estimate? What is your estimate of the mean weight of the individual acorns in the study? Well, remember that to estimate, we're going to take a look at the graph. So we're going to use our distribution of sample means to make an estimate. Let us take a look at our graph to make the estimation. So remember that we're looking for a balancing point, a typical value. So it should be, since it's normal, we remember that the graph is normal, is symmetric. And the center is around 3.75 grams. 3.75 grams, okay, it's not that bad. Using the center of the distribution. And here we have 3.75 grams as the mean weight, the center or typical value. Question 13 says, well, sample means are estimates of the population mean. Remember that since we don't have access to all information about population, we take random samples, we find the numerical characteristics for the sample, and then we say that, okay, the population should approximately have those numerical characteristics. So a distribution of sample means is a distribution of estimates. Any deviation that exists between a sample mean and the population mean is an error. That's how we define an error. The actual measurement and the estimated measurement, the difference between them is called an error. This is why we call the standard deviation of all sample means the standard error. Well, estimate the standard error of distribution of sample means from the previous problem, and B, compare the standard error to the standard deviation of 400 individual acorn weights. Well, let's take a look at our data. This is our distribution. Okay. What do we see here? The mean or the center is here. And remember that since we have a normal distribution, we expect these are 1 standard deviation, 2 standard deviations, 3 standard deviations away from the mean, away from the center. So the difference between these two numbers should give us the number that we're looking for. So you might say, hey, 4 grams minus 3.75 grams should give me the standard error. So what is the standard error in this case? 5 or 0.3, almost 0.3. So you're doing just an approximation for the standard error. So approximately it's 0.3. Remember that we said if we work with individual weights, not the mean weight, we get more variability. So if we work with the individual weights, we get more variability. So in this case, the standard deviation, we expect the standard deviation to be greater than the standard error. So the standard deviation, SD, is larger than standard error. Standard deviation is larger, is greater than the standard error. That's one of the main reasons we're interested in finding the means instead of working with individual weights or individual data. Let's move on to the next page. Well, in this page, what do we have? The simulation was conducted 2 more times. Well, using different sample sizes, we repeated the simulation. Each time, 500 samples were collected. So as you can see, we increase the number of samples. One simulation used samples of size 25, only 25 in each sample. And the other simulation used samples of size 100, increase the number of samples. Remember that you're interested in having more data in our samples. So smaller samples, okay, it's good, but it's not good enough. But when we increase the sample sizes, it means that the result is much better. It means that we get less variability. Okay, perfect. So these are our simulations. A, which of the above graphs do we believe represents sample of size 25 and which one represents samples of size 100? Well, we're a statistician. By looking at the graph, we know that when we have more variability, it means that we're not that happy. It means that the sample sizes weren't large enough. So this distribution with more variability, with more spread, representing samples of size 25. And as you can see, you have less variability, less spread. So it means that we use samples of size 100, less variability. Estimate the standard error of the two histograms above. Well, okay, let's take a look at our center. Our center is approximately here. So this is going to be our center, 3.7, just approximation. So the center is 3.7, and we're looking at the distribution, 1 standard deviation away from the mean, 2 standard deviations away from the mean, and so on. So it seems like we are dealing with the standard error of about 0.20. Now we can just take a look at these differences here, differences between these numbers, and it seems like the standard error is about 0.20. However, when it comes to less variability, we expect the standard error to get smaller and smaller. Well, let's take a look at our center. Suppose the center stays the same. Center, 3.7. So, well, if we check the variability, it's not going to be exactly the difference between these two numbers because it's now smaller than this distribution. This distribution shows that, hey, the difference between these representing the standard error. But this guy is smaller. You can say that, hey, the standard error is approximately 0.10. Less variability, smaller standard error, just by estimating, approximating the difference between the center and the data. 1 standard deviations, 2 standard deviations, 3 standard deviations. Approximately is 0.10 or might be smaller. But to get the exact value, we need to use software, our calculator, Excel, SAS, or Python, and different softwares that help us to calculate these precisely. See, what relation do you observe between sample size and the value of the standard error? Of course, the smaller the sample size leads to larger standard error. So, smaller sample sizes results in larger standard error or variability, larger standard error. Or you can say that, hey, larger sample sizes result in smaller variability or standard error. That's the relation and connection between sample sizes and the standard error. They have reverse relation. Smaller sample size, larger standard error, more variability, and larger sample sizes result in smaller standard error or less variability. So now we're going to talk about T distribution. Previously, we have seen that under certain conditions, the sampling distribution of sample means is normally distributed. As with any normal distribution, we are able to standardize a distribution of sample means by finding z-scores. We can do this if we know the standard deviation of population. So remember that z was x minus mean divided by standard deviation. The mean of the population, x minus mu, divided by standard deviation of population. Naturally, we're interested in answering this question, that what if sigma or population standard deviation is missing? Of course, we cannot find z, but instead of z, is there anything else that we can use? We're going to answer this question here. In this lesson, we will confront the reality that population standard deviation are rarely given to us. So in majority of cases, the population standard deviation is missing. Not knowing the population standard deviation influences the way we perform statistical inference regarding a population mean. Well, recall that when sigma is given to us, remember sigma is population standard deviation. Suppose we have a population whose standard deviation sigma is given to us. If the population is normal or the sample size is large enough, larger than 30, a sampling distribution of sample means is approximately normal. So if we have a population and we take samples from that population, calculate the means of those samples and construct a new distribution, that distribution is approximately normal. In this new distribution, we can find the standard error, which is denoted by sigma sub x bar. It is equal to the standard deviation of population divided by square root of sample size. So this is standard error of this new distribution, which is equal to standard deviation of population divided by square root of the sample size. That's how we can calculate the standard error of this new distribution. Then the standardized value, or our z-score, is equal to x bar minus mu divided by the standard error, which is sigma over square root of n. So we are changing the distribution. We cannot follow the previous formula. This previous formula for z was related to a distribution of x values. Now that we changed our distribution to sample means, we have a different z-score. This z-score is for the new distribution. What distribution? The distribution of sample means. So z is equal to x bar, the mean of the samples, minus the mean of the population divided by the standard error that we calculated here, sigma over square root of n. Since the sampling distribution is normal, the distribution of the T statistic, Z statistic, is also normal. In this case, the standard normal distribution describes the variability in the test statistic. Well, what if sigma is not given to us? This is our next stop. When sigma is given to us, everything is crystal clear. We can find a standard error, we can find z, but the main question is, what if sigma, or population standard deviation, is missing? Which formula we're going to use? Are we allowed to use z? Remember, when you're calculating z, on the denominator you have sigma, which is the standard deviation of population. What if we don't have the standard deviation of population? In most situations, we do not know the population standard deviation. Well, another way of saying this is that sigma is unknown. The only option available to us is to approximate sigma using sample standard deviation, which we denote by S. So population standard deviation denoted by sigma, sample standard deviation denoted by S. So when sigma is missing, we try our best to use sample standard deviation to approximate sigma. To do this, we need to substitute S for sigma, but we're not allowed to use Z anymore because it's not going to be the same. Very well. In our next page, we're going to continue talking about the case that when sigma is missing. So when we make this substitution, the standard error of sampling distribution is estimated by S over square root of n. S, remember, S is the sample standard deviation divided by square root of the sample size. Well, a test statistic for a sample mean is now x bar minus mu divided by S over square root of n. Since the sample standard deviation, or S, varies, it changes from sample to sample, and only approximate sigma, its use in the test statistic calculation introduces additional variability in the test statistic. The added variability means that the distribution of the test statistic is not normal. Well, the test statistic actually varies according to what we call the student T distribution. Student T distribution. So again, recall that when sigma is given, we're using Z, which is x bar minus mu divided by sigma over square root of n, when sigma is given. When sigma is not given, we're using T distribution. The T distribution describes the variability of test statistic, this new variable, which we denote by T, equals to x bar minus mu divided by S over square root of n. The sampling distribution of sample means is normal. We already know that. A sample standard deviation S is used to estimate the population standard deviation sigma. And this test statistic is called T statistic, not Z statistic. Z statistic is when we have sigma. T statistic is when we don't have sigma and we're using sample standard deviation. Like the Z statistic, the T statistic is an estimate. It estimates how many standard errors the sample mean is from the hypothesized population mean. Well, the T distribution is a family. It's not just one graph. It's a family of continuous probability distributions. The width of a T distribution depends on how much a sample standard deviation can vary. The amount of variability in a sample standard deviation depends on how many deviations vary freely when it is computed. Well, the sample standard deviation is computed using the following formula. S is equal to square root of the sum of deviations from the mean squared divided by n minus 1. The deviations from the mean x minus x bar are averaged in a sample standard deviation. When the deviations are added together, they always add to 0. That's why we have to square them so they don't result in a 0. Because of this, the last deviation summed in this average is not free. It is always the value that makes the resulting sum 0. There are n deviations from the mean, but only n minus 1 of these are free deviations. Well, next page gives us more description about the degrees of freedom. The variability of standard deviations depends on the number of free deviations in the sample standard deviation, or n minus 1. We call n minus 1 the degrees of freedom. Degrees of freedom. So degrees of freedom can be calculated using n minus 1. We find the sample size, we subtract 1 from n, and we call it the degrees of freedom. Technically speaking, each degree of freedom defines a uniquely associated t-distribution. It is important to know that the fewer the degrees of freedom, the more the sample standard deviation varies. So we would like to have n large enough. In other words, the smaller the sample size, the more the sample standard deviation varies, which we don't like. So the smaller the sample size, the greater the variability in t-distribution, which is not good. T-distributions have the following characteristics. First of all, t-distributions are all bell-shaped and symmetric with respect to the mean, and the mean is always 0. So the graphs for t-distributions, they are almost bell-shaped. They are symmetric with respect to the mean, which is equal to 0. So mean is 0, and you have bell-shaped graphs. These graphs are changing based on the degrees of freedom. So as you can see, if the degrees of freedom is 1, the graph is this inner graph. Then degrees of freedom is 2. You have this graph, which is getting closer and closer to a normal graph. If the degrees of freedom is 5, as you can see, your graph is getting closer and closer to a normal distribution, which is what we want. Each t-distribution depends on the degrees of freedom df. Again, df, degrees of freedom, is n minus 1. We need the sample size. We subtract 1 from the sample size, and we find the degrees of freedom. T-distributions have heavier tails and narrower peaks than the standard normal distribution. The area under each t-distribution curve is 1 or 100%. So this area below the graph is 1 or 100%. As the degrees of freedom increases, the tails are getting thinner and thinner. As the degrees of freedom increase, the t-distribution eventually approaches getting closer and closer to the standard normal distribution. When making inferences about a population mean, the degrees of freedom are equal to the sample size minus 1 or n minus 1. So as you can see, even though we are working with t, not z, but our graph eventually approaches to a normal distribution. So t is equal to x bar minus mu divided by s over square root of n. This is our t, this is our variable, and the graph related to that variable is one of these based on the degrees of freedom. Well, let us take a look at a couple of examples here. Try these. Well, okay. Let's see what do we have here. What is given to us? Researchers are very worried about how quickly sea ice is melting. If sea ice continues to melt, it is possible that polar bears will become an endangered species. That means that eventually there may be no more polar bears anywhere in the world. Polar bears use the sea ice for hunting and making their dens. Also, as the ice melts and erodes, there are smaller seal populations. Seals are the polar bear's main source of food. The further endangers the polar bear population. So biologists regularly visit Arctic regions to track the health and numbers of polar bears. Okay, well, one important measurement is the weight of adult male polar bears. So they collect the data. What are those data? The weight of adult male polar bears. Biologists estimate that the average weight of an adult male polar bear is approximately 475 kilograms. So what is given to us? The average typical value is given to us. For the questions below, assume that the polar bear weights are normally distributed. 1, suppose that 4 random samples of 5 polar bears are taken. So sample sizes are 5. We have 4 samples. In each sample, we have 5 weights. So this is sample A, sample B, sample C, and sample D. We have 1, 2, 3, 4 samples. In each sample, we have 5 weights. All of the samples have the same sample size. What is the appropriate number of degrees of freedom for this sample size? So recall that the degrees of freedom is equal to n minus 1. N is the sample size. Sample size 1, 2, 3, 4, 5. 5 weights in each sample. So it's going to be 5 minus 1 or 4. The degrees of freedom is equal to 4. Well, now, what is the mean and standard deviation of each sample? We're going to calculate the mean and standard deviation of each sample. What is the mean? What is the standard deviation of each sample? So let's use our calculator, enter this data in our calculator, and then calculate this. Let's turn on the calculator, clear the data here. I'm going to reset my calculator. Second plus. Reset all RAM. Second plus. Reset defaults. Now I'm going to calculate the mean and standard deviation of the first sample. So we're going to go to Stat, Edit, enter the values in L1, 466, enter 520, enter 512, enter 513, enter, and 498, 498. So you're going to go to Stat, Calc, one variable, everything is in L1, so it gives me X bar to be 501.8, and S is 21 point, if you round it, 55. 21.55. We're going to repeat this process for all of these samples. We're interested in finding the mean and standard deviation of sample B. When we're using our calculator, it gives us 456.8 with standard deviation 20.89. For the third sample, the mean is going to be 461.6 and the standard deviation is 25.32. And for the last sample, X bar, or the mean, is 491.6 with standard deviation is 14.54. Okay, now you're interested in finding the T statistic for each sample. This is our next step. Okay, very well. Remember that the T statistic for each sample, T is equal to X bar minus the mean divided by S over square root of N. So for each of these samples, we want to find the T statistic. Remember that the mean weight was given to us as 475. So we're going to use this as our mean mu, mean of the population. So the X bar for the first sample, we calculated that as 501.8 minus the mean, which is 475. Everything is divided by S. The standard deviation for sample A is 21.55 divided by square root of 5. Well, if we do the calculation using our calculator, it gives us just more space. This is equal to 2.78. The T statistic for the first sample. Let us calculate the T statistic for second sample. T is equal to X bar. X bar that we calculated for second sample is 456.8 minus the mean. Mean is 465, the mean of the population. I'm sorry, 475 divided by S, standard deviation of the second sample that we calculated is 20.89 divided by square root of 5. Again, if we do the calculation, t is equal to negative 1.95. What about the t statistic for the third sample? If we continue doing the calculation, it gives us x bar for 61.6 minus the mean for 75 divided by the standard deviation, which we calculated as 25.32 over square root of 5. This calculation gives us, well, negative 1.18. And finally, for the last sample, if we want to calculate the t statistic, it's going to be x bar. X bar we calculated in previous page is 491.6 minus the mean of the population mu 475 divided by standard deviation 14.54 divided by square root of 5. Well, after doing the calculation, our t is 2.55. Okay, we calculated the t statistic. Which of the 4 t statistics in the previous question shows a sample mean that is farthest away from the mean? It's far away from the mean. The t statistic is largest or the smallest. Between these 4 numbers, 2.78 is farther away from 0 than any of these. So, sample A. Which of the 4 t statistics indicates that the sample means are below mu equals to 475? Below, it means that you're dealing with negative numbers. On the left-hand side of 0, we have negative values which are related to sample B and sample C. Sample B and sample C. Which of the 4 t statistics indicates a sample mean that is closest to the mean? Which one of these numbers are closer to 0? Of course, negative 1.18 has shortest distance to 0. So it's going to be sample C. And finally, based on the sample statistic, which sample or samples should biologists and conservationists be most worried about? Which ones are away from the mean and they are showing less mean weight? If you take a look at these two are above the average. It means that the mean weights are above 475, which is a good indication. We are happy about these two. They are away from the mean and they are above the mean. We're happy about these two. What we concern about are these two because these are away from the mean and they are on the left-hand side. Less weight. But which one is farther away from 0? It's negative 1.95. This is away from 0 and on the left-hand side, so it shows less weight shorter. So it's going to be sample B. So if you want to think about it, here you have your 0, you have 1, -1, 2, -2. So 2.78 is here. 2.78, which shows that the mean weight is above the average. We're happy about that. We're not concerned about that sample. -1.95 is about here. It shows it didn't get close to the average mean, which is standardized at 0. So we're concerned about this sample.